Vector spaces provide the structural framework for a vast array of disciplines, from quantum mechanics to the high-dimensional data processing used in machine learning. In elementary physics, a vector is typically introduced as a physical arrow, an object with a specific magnitude and direction existing within a three-dimensional coordinate system. Functional analysis requires a broader perspective. Here, an entire continuous wave function is treated as a single point, a solitary element within a much larger abstract space. To treat a function as a point, we have to move past physical geometry and isolate the underlying algebraic properties that make linear operations possible. In this rigorous context, a vector is defined by its behavior. It is any mathematical object that obeys a specific set of operational rules or axioms. We are going to build the intuition behind these spaces, defining their axioms, exploring Erwin Kreyszig's foundational examples, and examining the structural logic of mathematical dimension. Removing the requirement for physical coordinates allows us to apply the tools of linear algebra to infinite dimensional problems. A vector space is built on two components, a set of elements, x, and an underlying scalar field, k, which usually consists of real or complex numbers. Interactions within this space are limited to two specific operations, vector addition and scalar multiplication. These operations are governed by axioms like commutativity and associativity. These ensure that the order in which we add vectors, or how we group them, does not change the final result. The space also requires a zero vector to act as an identity element, and an additive inverse for every vector, guaranteeing that every movement in the space can be precisely reversed. It is important to note that the zero vector is not always the number 0. Depending on the space, it might be a matrix of zeros, or a function that is 0 across its entire domain. Additional axioms for distributivity and scaling ensure that scalars interact with the vectors in a predictable, uniform way. These rules are not arbitrary. They are the minimum requirements to maintain a consistent linear structure. If a set of objects passes these algebraic tests, every theorem of linear space can be applied to it, regardless of what those objects represent. We can define the boundaries of a vector space by examining sets that fail these requirements. Take, for example, a line in a two-dimensional plane that does not pass through the origin. This set fails the requirement of closure. If we add two vectors that lie on this offset line, the resulting vector falls outside the set. It no longer belongs to the space we defined. We see a similar failure in the set of all polynomials of exactly degree 2. If we add x squared plus 2x to negative x squared plus x, the quadratic terms cancel. The result is 3x. Because this is a first-degree polynomial, it has exited the set of second-degree polynomials, violating closure. Without closure, the algebraic structure is inconsistent. We lose the ability to apply theorems because our operations can lead to results the set cannot contain. We can now apply this axiomatic framework to the foundational examples found in Kreyszig's text. Examples 2.12 and 2.13 cover Euclidean and unitary spaces, where the familiar axes of geometry expand into n dimensions. Example 2.14 introduces C of AB, the space of all real-valued continuous functions on a closed interval. Addition here is defined point by point. At every value of t, we add the outputs of two functions to create a third. Because the sum of two continuous functions is itself continuous, the set maintains closure. In this space, each unique function, the entire curve across the interval, is treated as a single point. Kreyszig also defines the sequence space, L2, in example 2.15. Here, an infinitely long sequence of numbers acts as a single vector, with addition performed term by term. To ensure this space remains valid, we rely on Minkowski's inequality. This proves these infinite sequences converge and remain within the boundaries of the space. The same algebraic logic that governs coordinates on a page also governs the infinite complexity of these function and sequence spaces. Within these parent spaces, we often find smaller, self-contained structures called subspaces. We describe the span of a set as the collection of all possible linear combinations that its vectors can form. If a set of vectors is linearly independent and spans the space, it's called a basis. The number of vectors in that basis defines the space's dimension. While many matrices operate in finite dimensions, spaces like C of AB are infinite dimensional, requiring an infinite number of basis elements. Kreyszig's theorem 2.18 states that any proper subspace, Y, of an n-dimensional space X must have a dimension strictly less than n. We can verify this through contradiction. Suppose the subspace Y has the same dimension, n, as the parent space X. That would mean Y contains n linearly independent vectors. Since these vectors are independent and exist within X, they are sufficient to span all of X. In this case, Y would be identical to X. For Y to be a proper subspace, meaning it is a subset and not the whole, it must possess fewer degrees of freedom. Dimension serves as the measure of a space's freedom. As we move into infinite dimensions, we must look beyond basic algebra and introduce topological tools to measure distance and convergence. We have successfully moved the concept of a vector away from the geometry of the physical arrow and into the realm of pure algebraic axioms. This shift allows us to treat complex objects, like continuous waveforms and infinite sequences, as simple points within a structured space. However, these spaces currently lack a way to measure distance. To address that, we must equip them with a norm, which leads to the study of Banach spaces. If you want complete explanations of books like Kreyszig, Rudin, functional analysis, linear algebra, real analysis, and topology, then don't forget to like, subscribe, and share this video. Comment below which theorem, proof, or chapter